world.
All right, everybody. Thanks for getting seated here. We have an exciting talk in front of us. We have Don Scott and Michael Green from Hitachi Solutions America, and they're going to give an exciting talk about their comparisons between Databricks and Snowflake for machine learning.
Thank you so much.
Thank you. Hey, everyone. We got a good-sized group in here today. I'm Michael Green. I'm with Hitachi Solutions. This is Don Scott.
Nice to meet everyone.
It's great to be here. We're excited to be at DAIS. I think, Don, you've been here a couple of years now.
5, 6 years.
There you go. There's stickers downstairs you can get for that.
I got to get them.
You got to go get one. So I'm a senior data scientist at Hitachi Solutions America. I have a PhD in artificial intelligence from New York University at their Tandon School of Engineering. I have a bunch of papers in AI. This is Don. We're colleagues.
Nice to meet everyone. I run new product development at Hitachi Solutions, really focused on how do we take the things that we do for all of our customers again and again and again and again, and make that more of a packaged offer, something that you can deploy quickly, easily, and keep up to date. My mic is not working.
Are you on?
It's working okay. All right, the voice, good enough. For those of you that aren't aware of what Hitachi is, and it's a very large company. We do everything from nuclear reactors to data estates. Hitachi Solutions specifically is really an Azure-centric SI, and our group is focused on figuring out how we steer customers and having kind of a biased approach, but making that bias based on facts, and then reevaluating those facts from time to time with benchmarks such as this one to steer our customers to the right solutions. So today we'll talk a little bit about how we made some decisions around our own AI platform and how we did that with Hitachi's existing investments in TPC. We'll talk a little bit about data science and the TPC-AI benchmark generally. Then we'll dive into Databricks and Snowflake performance on single node and multi-node. And then we'll talk a little bit about how you guys can test this yourself. You don't have to take our word for it. Download the repo, try it out in your own clusters, and maybe even make improvements. So if you disagree with anything that we found, we're really inviting input from the community. So we'll talk about that as well at the end. Without any further ado, Michael, why don't you take it out from here?
Sure. So let's talk first a little bit about what the TPC benchmarks are, for those of you who aren't familiar. TPC stands for the Transaction Processing Performance Council. There's a website that you can go check out in case you haven't seen that before. Full disclosure, Hitachi sponsors it along with all these other companies that you see on the screens behind me. They have benchmarks for artificial intelligence, for IoT devices, for virtualization, transaction processing, decision support, big data. These are just actually a few that are on their website. We're just going to talk about really the AI piece today. But you may be asking, why are we using the TPC to benchmark? This stuff has been around forever, right? The TPC has been around since like the early 2000s, I think even before then. It's because data and AI have histories in benchmarking, right? If you even go back to the 80s and the 70s, when these algorithms were first getting invented and created, we've been benchmarking them to assess their performance to say which of these algorithms is better than the others for a particular use case, right? For example, for computer vision, we use things like ImageNet. There's other big AI benchmarks out there, especially around NLPs and large language models, right? Very relevant for this particular DAIS's topic. So like in the past, what TPC has primarily been used for is Hadoop, right? That used to be the big data processing giant of the early and late 2000s. When you measure the speed and the cost of data flow, each of these benchmarks, the AI one, the IoT one, the DS, the DI, they all drive several hard performance numbers, which make them really good candidates for continuing their benchmark journey into the modern data estate world. And they provide this solid framework that we can use while making it more relevant for the cloud, right? They generate the data for you. They have the use cases available. There's guardrails up, so you're not venturing too far outside of a use case. All that stuff is already taken care of, so why not try to bring it up?
And just like everything else, you may be optimizing in your business for latency. You may be optimizing for cost. So there's a lot of different metrics that are calculated. And in this talk, we'll go through some of those. but there's obviously a lot more detail behind the actual assessment. So we have a white pager that we can distribute for those that are interested in really the detailed stats.
That's right. So let's get into it. Let's talk a little about data science and the TPC-AI benchmark. So I am a recovering academic. I'm also a lecturer at NYU, and so I would be remiss if I didn't go through a couple definitions with my audience. I can't help it. We're going to talk about a couple different machine learning types today. So some of you who are familiar with data science may already be very familiar with these three types of data science solution spaces. These are not the only ones out there, but we're going to localize our experiments that we're going to talk about today with you all to just these three. These are classical machine learning, natural language processing, and computer vision. So classical machine learning, right? You're probably working with structured, tabular data, maybe even semi-structured data like CSV files or JSON files, and you can perform things like classification, regression, and forecasting problems on using classical machine learning algorithms. There's also natural language processing. This is actually what LLMs are doing, right? It's natural language. You're using words, sentences, or dialogue. You use it for speech recognition, for translation services, for text comprehension, and even sentiment analysis. And lastly, we have computer vision. This is when you're using images or video. It's very unstructured file formats. And you might use this for item recognition, labeling, or facial recognition. We're going to actually talk about a use case on that today, and image and video generation. So when you start a data science engagement, I'm going to just try to carve through the journey here at a very high level. You typically start off in a notebook, probably a Jupyter notebook. That one's one of my favorite types of notebooks to use. Databricks also has notebooks that you can use. They're great. They're collaborative. We like them a lot. But you start off with one model that you're experimenting with, and this model is located on a single machine, right? We called it single node experimentation. Now, why would you use single node? Well, it's really easy to set up. You could run it on your own computer. You literally hide Jupyter Notebook in your command prompt, and boop, pops up for you right there on a Mac. You can iterate very quickly because you can run these cells either in an iterative fashion or even out of order, make a small tweak, rerun, and it's very cheap. Right? You can run this on your own laptop. You can run this on a VM in the cloud. Now, if you are developing large models, or you're using lots of data, or you're finally out of a zone where you're more comfortable not using a single node machine because you want to scale up, you're going to use what we call a multi-node deployment. In fact, you might even use this in production for inferencing, right? Now, why would you want to do this? Because using more machines, more compute means more power. Some of the largest language models today require hundreds of GPUs in order to train. They require a lot of data, right? Terabytes and petabytes of data to train on, which requires a lot of memory, a lot of disk space, a lot of compute. But the infrastructure can be difficult to set up when you're using multi-node deployments. Now, we're going to talk about two different kinds. I just want to go through really briefly. When we're talking about multi-node, we're talking about one model across many different machines. The most popular ways to do this is called model parallelization or data parallelization. In both of these cases, these nodes have to communicate with each other during the forward and back propagation stages of a network. Okay? And that's very, very technical, so I'm going to try to keep it brief. On model parallelization, you're taking one model and you are sharding it across nodes, and you're taking a single unified data set, and these nodes are communicating with each other as it's stepping through the different layers of the network. During backpropagation, that is reversed, and that's how the network trains. Okay? Again, the nodes have to communicate. For data parallelization, instead, you're going to take your model, you're going to clone it on each of your nodes, you're going to have a copy of your model on every node, and you're going to shard your data across your nodes. So each node is going to get a subset of your data. They go through a batch, they figure out their gradients at the very end, pass that all the way back up, and we resurface each clone of that model on each node. But in both of those cases, again, the nodes have to communicate with one another, and I'm going to keep harping on that. That's going to be a theme. So how would we do this on Databricks? If I wanted to do single node training on Databricks, I would use pandas or Spark data frames or even NumPy arrays. I have delta table support if I want to use delta tables. You can use whatever machine learning libraries that you want. If it's NLP libraries, deep learning libraries like TensorFlow, Keras, PyTorch, scikit-learn, you just envision whatever it is, and you can probably just install it on the cluster or just within your notebook. Depends on whatever you want to do. And you'd set up a single instance cluster in your Databricks workspace, dedicated or jobs, and run your notebook on it. It's really simple. It's that one over there on the right-hand side. Now, if you want to use a multi-node deployment, that's also really easy, right? You need to use a Spark data frame. You could use Ray. You could use the Spark Torch DDP integration, which is brand new. You can also have Delta table support with your multi-node deployment. You can use the Spark ML or Petastorm or Horvath versions of those same machine learning libraries that you want to use. And you set up a multi-node cluster in your Databricks workspace, or you can use jobs to run your notebook on. It's barely a change. It's a couple lines of code, that's really it. And now all of a sudden you have all that power available to you. Now, if we look at how you do this on a Snowflake environment, the first thing you need to know about Snowflake is that it's built on SQL. It's a data warehouse built on SQL. I see a lot of phones coming out. That's good. I spent a long time on this graphic, so I'm really happy to see that it's getting appreciated. So on the very top here, we have our single node training, and on the bottom, we have a multi-node training. And the first thing you're going to notice is that this looks a bit more complicated than the slide that I just shared with you. When you were talking about training within a Snowflake data warehouse, you have to train with UDFs or stored procedures because it's a SQL environment. It's not built to natively handle Python the way that Databricks is, right? Snowpark can build the training function in the user's own IDE. You can send that function along. It will be translated to SQL within the Snowflake data warehouse. And both the data in the model are contained and trained entirely within the Snowflake execution environment. But you can only train it this way on a single node due to how SQL manages UDFs and stored procedures. When you're using UDFs and stored procedures, the nodes can't communicate gradients. You're not able to train models in a multi-node fashion within a Snowflake execution environment. And UDFs are only recommended for models and data sets that would take less than a minute to train because on Snowflake, the default time for a UDF execution, at least at the time that we ran this benchmark, was 1 minute.
Yeah, it sounds like a ridiculous limitation, and it is.
Stored procedures are limited to a 1-hour execution time. So I think yesterday when we were watching the Mosaic keynote, we saw some models that were training for days. That wouldn't work on a Snowflake execution environment in single node. If you want to do multi-node training, I'm afraid to say that we weren't able to figure out how to actually do this inside of a Snowflake data warehouse. We actually had to have a second cluster. That was our compute cluster for training. We used a Spark cluster, but it requires a second compute cluster, again, because these nodes can't communicate inside of a Snowflake data warehouse. Now, you can use Snowpark or the Spark connector to get your training data and treat Snowflake purely as a warehouse for your data, but you aren't able to actually do the training inside of it. In either of these cases, MLOps isn't included natively inside of Snowflake, so you're going to have to use another third-party service like MLflow or Dataiku outside of the Snowflake execution environment in order to do things like model registry or experiment tracking. So if we review the artificial intelligence strategies, going to try to combine those definitions of different machine learning types that I spec'd out before. If we're talking about Databricks, Databricks supports multi-node and single node pretty easily. You have full control of the libraries you want to install on a cluster, how big you want your clusters to be, and even the instance types of your worker nodes and your driver nodes inside of your Spark compute. In general, Databricks always succeeds, whether it's single node or multi-node, and no matter what use case. If we're talking about classical machine learning, computer vision, or natural language processing, it just works. Meanwhile, if you're using Snowflake, you're going to use the Snowpark library for communication with Snowflake or the Spark connector. And single node was failing for us for tabular data over 1 million rows using any of the use cases due to memory and time constraints set by Snowflake for UDFs and stored procedures. We had limitations on using very popular computer vision and NLP libraries in order to do data processing inside the Snowflake execution environment. And to perform multi-node workloads, you have to use a third-party compute environment, which means you have to worry about an additional cost and performance latency. We're going to get into that a little bit later.
Mike, one thing, just
sure.
for the sake of fairness, we expect that Snowpark, Snowflake will improve the performance here. But these were pretty substantial limitations that we were finding even when we were using the smallest sample sizes that we could with these benchmarks.
That's right. That's right. So let's talk a little bit about TPCx-AI. So TPCx-AI is a benchmark inside of the TPC benchmark standards. It's an end-to-end AI benchmark standard. It has 10 different use cases that measure pipeline efficiency. Each of these use cases is unique. They try to match them to a retail type business. So you're going to notice a bit of a retail spin on some of these use cases if you've ever checked out that benchmark before online. It tracks the loading, processing, training, and serving speeds of your models. So it kind of incorporates the whole life cycle of a data science project. And it creates data sets for you with realistic data for each of these use cases. So you don't actually have to build the data sets. You just have to run a line of code. And then you have to go store it somewhere. Now, these data sets are scalable to different sizes. You can set something called a scale factor. We decided to scale these data sets from 1 gigabyte to 100 gigabytes and measured 1, 10, and 100 just to see how that would impact performance and cost for each of these use cases. Now, we restricted our experiments to just a subset of these. We had a limited amount of time to actually run these, and we picked 4 of them. We targeted them specifically for their variety in the ML solution space. Some of them were classical machine learning, some of them are natural language processing, some computer vision, and they're using different structured and unstructured data types and data point sizes. Now, these are the 4 that we used. We had a recorded conversations to text use case. We had an item price forecasting using a description. That's an NLP use case. We had a predicting a customer's next purchase use case. That's a CML use case. And we had a recognizing repeat customers using their face. So that's a facial recognition problem. That would be your computer vision use case. Let's talk about the stuff everyone's here to see. So in general, if it wasn't already iterated to you before, we had a lot of issues with running Snowflake for single node because it wasn't working with a lot of common AI use cases for a variety of different reasons. When we tried to run the natural language processing and computer vision benchmarks, we were running into library installation requirements that Snowflake execution environment wasn't allowing us to install because it didn't come off the shelf with that execution environment. You can't install stuff that's missing from their image. We are having issues with the classical machine learning benchmarks because of memory and time restrictions, right? Again, founded on SQL architecture means that you have to use stored procedures or UDFs in order to actually run Python code inside of this environment, and that means you're limited by memory and time. Below, you can kind of see, based off of the each of the use cases, exactly what failed. I don't want to hover too much on this slide, but I think you guys get the idea. For what we could run, Databricks tended to be dependable and faster for these single node experiments. Again, the audio transcription, next purchase, and customer recognition scenarios kind of failed on Snowflake, but for what did succeed, this other CML use case, for the 1 gigabyte and 10 gigabyte data set sizes, Databricks was faster by a significant margin as we continued to scale up in data set size. And this also translated over into costs. Databricks was also cheaper than Snowflake for this use case in both 1 and 10 gigabytes. Now, to keep all this in mind, full disclosure, we are using jobs compute in order to calculate these Databricks costs.
These costs also do not include any of the changes that occurred this week and have been rolled out over the past quarter. So you may find that there is a little bit of variation when you download the repo and try it yourself. But in general, these are pretty wide gaps.
Yep. Now, these are the multi-node costs. I was starting to run out of slide room, so I didn't put the performance ones in here, but they look much less the same. And like Don was saying, we do have a white paper out in case you want to see, you have questions about this more in detail. Please come up to us afterwards. We're very happy to share it. But for multi-node across all of these use cases, keeping in mind we're running the compute part of Snowflake's experimentation on a second compute environment because we can't run it inside of the Snowflake data warehouse. Databricks is equivalent or cheaper for multi-node deployments. And again, this price differential is increasing with scale size. We see that especially in the price prediction and in the customer recognition scenarios. So, high-level overview of the multi-node cost breakdown. Snowflake makes it really difficult to run multi-node natively. It's just how the SQL architecture works. Again, we hope that there's some stuff rolling out soon with Snowflake that will make this easier, but for right now, Databricks just works really, really well. You only really have to worry about the cloud infrastructure costs. We prefer Azure. We're Azure partners, so we like running things on Azure. But there may be some AWS folks or Google Cloud folks out there. And you only have to worry about the DBUs that you're incurring with the cost of the Databricks platform.
So for all these reasons, we decided to really bias and push our customers towards using Databricks really for the end-to-end stack. Now, how most customers that are using Snowflake and insist on using Snowflake use it is they end up pulling and pushing the data to and from a platform like Databricks to actually do the AI ML. So you end up double paying on that, and there's a lot of other talks this week that have talked about the overall performance picture with these alternative tools on data engineering workloads and AI. But it's fair to say, when you look at just the AI workloads and then you add on the fact that now you're going to have two systems, you're going to see a really heavy skew on the cost side. So in short, we found Databricks was better for those single node workflows. It was a lot easier for us from a developer experience. Keep in mind, your developers are probably your most expensive asset. So that's really something that you're going to want to think about when you're talking to your managers and your CIOs, et cetera. We found that Databricks was cheaper and more reliable for the multi-node experience as well, and that when you compare multi-node workflows, there really wasn't a comparison, right? And this isn't surprising. Spark has been an AI ML platform for decades, and there's a lot of library support, and a lot of these things have just been worked through. Tacking in AI capabilities into a traditional database solution, including a fairly well implemented one like Snowflake, isn't something that's very easy to do from an engineering perspective. So from an overall setup perspective, we just could not recommend Snowpark at this time for most of our customers actually seeking to do AI ML. So looking forward, we wanted to provide a centralized location for actually fellow partners to test this out themselves and to start to contribute, because we all need this capability. We want to see, as all of these cloud platforms adopt and upgrade and release new features, we need a way to kind of cut through the marketing and see what is the actual performance so that we don't make mistakes with our customers and their workloads. So we actually have published a public repo, and we'll have a QR code in a second on Hitachi Solutions GitHub page, which will allow the community members here to download these data sets, run them on your own clusters. You don't have to trust us. You can look at how we implemented these 4 use cases, and I believe there's some new submissions as well. We have the data engineering benchmarks up there as well. And we hope that the community will latch onto this and help move it forward together with us. So here is that QR code if you want to check it out. I would say this is a moderate engineering task. So if you want to go spike on this, probably take a week or so of your engineers to do it. You can check out the TPCx-AI benchmark, which we talked about today. There's also a DI benchmark and a DS benchmark. So you can have some fun with that and experiment with those comparisons. We're looking forward to expanding those use cases. So we did 4 out of 10. There's a lot more coding work to do. So feel free to come in, maybe do a spike, do a use case. We'll love you. I'll buy you dinner. And we can work together to kind of get those published on a recurring basis. So again, all this is really we're doing it because we need to provide advice to our customers on how they should build these architectures. And then we want a little bit of a foundation to stand on when we make these opinions, so that we're not just fanboys of one project or another. And we're doing this because we're deploying a tool we call Empower, which is our managed data estate offering. Think of it as PaaS on PaaS for Azure customers, where we lay down, yes, infrastructure in that first week, but we also do things like push Spark packages and streaming connectors and a lot of other things that we see our customers doing time and time and time again, and kind of give their engineers a little bit more efficiency across the whole stack, from data acquisition down to incremental publishing to Power BI, et cetera. So a lot more of Empower on our website if you're interested in that. And if you'd like our white paper to kind of break down these numbers and go a little bit level deeper, feel free to reach out to us on email. We'll send you the PDF, and you guys can dig in to your heart's content. Here's a QR code if you're interested in how we can help you deploy Unity Catalog and Databricks more generally.
Thank you very much, everyone. We appreciate it.
Thank you.